Hi everyone, so today we're looking at part 2 of Le Chatelier's principle, and this is looking now specifically in the change in temperature. So the previous lesson was a change in concentration, now this is the change in temperature. So when we look at the change in temperature, we can have two different types of reaction. We can have endothermic or exothermic. So when we have endothermic, we have heat as another reactant. So that is on the left side of our equation, and exothermic is heat as a product. So it's on the right side of the equation. So that's going to be really important to recall in the future. So first, we're going to start with endothermic reactions. And the way we know this is endothermic is because heat is a reactant. So we are going to assume that we have a test tube and it contains all the reactants and products at equilibrium. So if we have the reactants, if there's more reactants, then it's pink, and if we have more products, it's blue. In this situation, the color is pink, which means that we have more reactants than product at equilibrium. So we have our concentration table. This is where it is at equilibrium. Now we add heat to that test tube. So when we add heat to the test tube that is pink, now you are adding heat to the reactant side because it is pink. So because it is pink, we know it's mostly reactants. Plus, it is an endothermic reaction. Heat is on the reactant side, so we're adding it to our reactants. So when we add heat, we are increasing the reactants. So as the reaction is trying to relieve the stress, what it does is reduce the reactants by shifting to the right. So as you continuously heat it, it starts to change color to blue. So the previous table now, what it's going to show us is how we're trying to reach equilibrium. So we have COH2O6, okay, because that's a reactant, as well as Cl, and it was mostly reactants. We are actually going to decrease our reactants and increase our products in order for it to change to blue, which is what's happening because we're heating it. So you can see here in the table that as we heat up the test tube more, the reactants decrease. So we have our reactants decrease and our products increase. Once again, water was a product that we saw in that equation. Water is a liquid, and therefore, based off of previous lessons, we know that the concentration of water does not change. Okay, the only thing that changes is the amount, so we're not looking at that. So this is concentration, so we're not going to add it onto our table because it stays the same. So based off of this reaction here, we are heating up the test tubes going from left to right, so therefore our products increase, our reactants decrease, and that is showing our Kc change. Another example, same sort of equation, okay? But now let's assume that they all are at equilibrium again, but now the color is blue. So because it's blue, we now know there's more products than reactants. So everything is at equilibrium based off our chart. If we now put it into an ice bath, okay, so opposite of heating, we put into an ice bath, we're removing that heat, and the heat is on that reactant side, so think of it as we're reducing our reactants, we're lowering our reactants. So because the reactants are decreasing, that means that we are going to shift to the left in order to cool it down to an actual color of pink. So because we're cooling down, okay, what is going to happen? Since the reactants are decreasing, we want to actually increase those reactants because they're decreasing. So what's going to happen is that we're going to increase those reactants up in reverse, and our products will decrease, which you will see here. So that means our products will decrease, our reactants will increase, and therefore our Kc decreases overall. Now let's look at another example. So this example 3 and 4 demonstrating exothermic reactions because heat is on the product side now. So we have a test tube with more N2O4 than NO2, and it is seeing if it is at equilibrium. So what happens to the concentration of NO2, N2O4, and the Kc if the temperature is increased? So we're going to add heat to the test tube. So right now it is at equilibrium. Once we add heat to the test tube, we are adding heat, which means the heat is already on the product side. So you're already heating up the products. So because the products are already heating up, we want to decrease that by shifting to the left. So we want to reduce our products, we shift to the left, and once we shift to the left, we relieve that stress, we reduce our products, we increase our reactants. And therefore, our Kc, products decrease, reactants increase, and therefore the Kc decreases. Okay? And then last but not least, we have the following reaction. We're looking at the products, reactants, and the Kc. If we remove heat, so now we cool it down. So based off of this equation here, we have our heat as our product. Once again, when we look at it as our product, we're cooling down the test tube. So that means we're removing the heat. So because the heat is on the product side, we are decreasing that heat because we want to remove it. So because we are decreasing our products overall, we are going to shift to the right because we want to release the stress of the products by increasing it and decreasing our reactants. So as we do so, we're just going to skip over that one page. As we do so, you can see the graph here. Our products will increase. Okay, so our PCl5 increases. Our reactants decrease. Both reactants decrease. And because of that, our Kc increases because our products are increasing. Okay, so exothermic and endothermic are completely different types of reactions. They're kind of the opposite of one another of how they work. The Kc value changes depending on what reaction we're looking at and if we are adding or removing heat. We can do something by adding a catalyst. So a catalyst we've seen probably before in other classes, but a catalyst is what increases the rate of both the forward and our reverse reaction, because that's what we look at, forward and reverse reaction. And it changes them by the same amount. So it doesn't matter if we go forward or reverse, it will change it by the same amount, and it allows our reaction to reach the equilibrium as fast as possible. Once again, it doesn't affect the amount, doesn't affect anything like that. It just speeds up the reaction to reach equilibrium faster. So catalysts are often used to speed up a reaction, and that's what it's for. And they're quite often used, and you will see it here and there as we go through, obviously, the course and your other courses as well. But note that catalysts are used to speed up a reaction